Can you see now on YouTube? No. Sì. Ok.
È liesimo, se questi sono tutti. No, perché adesso l'uso quindi può stare liesimo. Quindi sono possibilità che oltre per RT per terra normale, quindi R per Z.
So, for the online students, I don't know where the streaming ended. So I wanted just to recall that we presented the prediction function, and in particular you were asked to focus on the Jacobian A and on the Jacobian B, provided that you could use the initialization with the identity function, because in this special case the transition function of the landmark is equal to the identity, as the landmarks remains fixed, and therefore we can initialize the A matrix with the identity and then focus on these three elements, on the elements of the first three rows, first three columns, by using this MATLAB syntax. And the same holds for the B matrix, where we have all zeros other than for the B matrix, where we have all zeros other than in the first three rows, so we'll use the MATLAB syntax in this way. Then here you were asked to fill the control noise as usual and the predicted sigma using the equations of the extended Kalman. So if you check the equations of the extended Kalman here and compare it with the solution line 69, you will see exactly the same expression. Okay. Now in a few minutes I will present the correction. So, for the guys online, Professor Grisette is repeating the explanation about the Jacobians, okay, I am going at the Regia to check whether something
that it
happened.
comes.
Okay.
All right, so now the problem that we had was I have a robot in a certain position, we graph it to the work with its own covariance matrix. Like, let's extract this robot position as a random variable xr, which is normally distributed according to a mean mu r and a covariance sigma r, right? Where this is the portion of the covariance extracted from the global state of our camera filter. Okay? Then the robot performs the observation of a landmark. Let's say the landmark is here, right? And then, given that this is the reference frame of the work, we said that, so this is a ball, right? Let's say that we would like to populate our state with the new block, a new component of our state, a new variable, new dimension actually, that represents the new introduced landmark. Okay, guys? Clear? Let's call this variable xl. This block, this pair of coordinates. Right. And then, of course, I will have a certain noise in the measurement itself, but that lives in the measurement space. Okay. Now, my question is, okay, what is it XL? How do I put it in my state in general? And then the thing is that I say is like, you should propagate the noise in the robot position and the noise in the observation in order to get an estimate of the covariance matrix of this landmark, which presumably will be kind of larger than the covariance matrix of the robot position, because if you don't know where you are, also where you put the landmark, you don't know where you are. Okay? The question is like how to compute this covariance matrix over here, which will have dimension XL by XL. And the answer is, okay, let's say that I have a function g of xr z, this is z, zl, or z and master, that calculates xl, right? Is it visible? Let's say that I have a function like that. Clear? Very good. This function in our case is nothing else than take the robot position and express the measurement in the word frame, which basically means take the robot position, turn it into a transformation matrix, and then multiply the observation, which is a vector in the robot frame, with the position of the robot in order to get the position of the landmark, right? Rudely saying, our g of x will be r of rotation matrix of theta that multiplies z plus the translational part of the state, right? That's it. In our case, in this simplistic case, it would hold also in 3D, only that here you have three angles. Clear? Right. Now, the thing is that this is in general a nonlinear function. If it would be linear, this function over here. Oh, remember another thing, that also z is normally distributed according to a normal distribution that is mu z and sigma z. Right? Okay? Now, if I take this random variable and this random variable, and I consider the joint of the two random variables, so I just stuck them together, I could have a new, let's say, variable, which I call xz, okay, which is the stack of x and z. Clear? So xz, or give me a name. Xz looks like a product. Y, W, let's call it W. W is equal to x R and Z, right? W. No? What is W? If these two are normally distributed, also W will be normally distributed, being just the union of the two. Okay? They are independent, and so W will be normally distributed with mean mu R, mu Z, and with covariance matrix sigma R, sigma Z. Okay? Is that clear? Very good. Now, this is a random variable normally distributed. Could I just see this G instead of seeing a G made this way? I could simply say that XL is equal to G of W. Now, given that W contains both.
Why did we put the XL and Z in the same vector?
Eh?
Why did we put the XL and Z in the same vector?
They are not in the same reference. In the same matrix, you mean? What are we doing? We are just like, we have two variables, two independent dimensions, right? Can't we consider the variable that is the union of the two?
Okay.
Yes, we can.
Okay.
No? It's like, we do because we can.
Okay.
Okay. Now, this G of W can be in general, if G of W would be an affine form, then if G of W will be in the form G W plus B, then we could say that XL would be randomly distributed with a covariance with the mean G mu W G times mu W, and with covariance matrix G mu W plus B, sorry, and with covariance matrix G sigma W, where sigma W is this one over here, times G transpose. Agreed? Agreed or not agreed? Okay. Now, if we take G of W and we do the Taylor expansion, see the slides of the Gaussian distribution. If we do the game of the Taylor expansion, then we end up to this form. We end up that the G is nothing else than this capital G here is nothing else than the derivative of G of G with respect to delta to X and of G with respect to Z, stacked aside. Okay, guys? No? All right, now, let me go on. Let's say that we can express this function over here as G of mu W and G of mu W plus dG over the W times delta W. No? Where delta W is the difference between the mean and the evaluation point, which we call it delta W. The difference between the mean and the evaluation point has a zero mean as a covariance matrix which is equal to the original covariance matrix, which is going to be sigma W. Okay? So, at the end of the game, the G over the W is nothing else than the G over the X, and the G over the W, so the Z, right? Okay? Now, if you rework the terms, you figure out that you have the rule on the affine form. And the covariance matrix will be nothing else than given that the sigma is these block diagonal structures, you will have that the covariance matrix will be exactly equivalent as the covariance matrix of the predict set. So, it has the same shape. Okay? Or actually, it's exactly what we're doing in the predict set. We are propagating the control, let's say this way, the control and the current state to the next state. In this case, we are propagating a part of the state, which is the position of the lambda, the measurement, with its noise, to, instead of the next state, to the predicted landmark. Okay, guys? It has the very same form. So that's the meaning of it. And in order to assign the covariance matrix, then you will have to assign a covariance matrix which is equal to, let's call this A, and let's call this B. You'll have to assign the new landmark. So we might say rudely that XL is normally distributed with mean G of mu x, mu z, and with the covariance matrix A sigma x A transpose plus B sigma z B transpose. Okay? That's gonna be it. Do I have questions at all?
No, I hope that they will.
Okay. If you want to do it, cool. If you want to do it as a butcher, you just say, I see a new landmark, I give it a huge covariance, when I will reobserve it, it will become nice. Did I ask, now is it crystal clear or?
Clear.
Okay, please have a look at the slides on the Gaussian, because I think this is something, like you missed that one lesson, if I remember, you told me.
I watched it.
Yeah, but all right, I think I'm done. Oh, è entrato in sospensione questo buon portatile.
Sì, però questa è dice excellent connection.
Sì, sì, però toglilo dalla sospensione per sempre, possibilmente. Mi turba. Quando fai lezione la sospensione.
Ok. Per vedere se c'è ancora qualcuno. Cioè c'è il solito concurrent viewer. Giusto?
No, sì, c'è un commentare. Ok.
Ok.
Questa poi va rieditata, tagliamo il pezzo per faccio il primo spiegone.
Sì.
Tranquillità. Avete fatto tutti, ragazzi?
Non stiamo pieno di render.
Ok.
Spiego la fine. Correction.
Sì.
So,
Aspetta che inquadro.
Fox,
L'inquadratura è quella giusta? O?
sì. Okay, so I guess you can hear me and see me. So I will present the correction and ordinal landmark part. Now, in the correction function, you were asked to fill in the prediction of the measurement and the Jacobian. Now we will see it very quickly. First of all, you retrieve the number of observations, but this was done for you. Also, the state of the robot was retrieved for you from the me vector. Then the rotation matrix, its transpose and its derivative was computed already for you. So then for every observed landmark, if it is not the first time that we see it, meaning that there is an entry which is non-1 corresponding to its identifier, then we can use it to retrieve the position in the state vector. If you check, this formula exactly gives you the position in the state vector given the number of the state in the landmark vector, the number of the landmark in the state vector. Then we have the actual computation of the prediction of the measurement, which is given by the usual formula, meaning R transpose position of the landmark minus translation vector identifying the robot position. The only thing that you need to notice is that in this case, instead of having here a value that represents the position of the landmark in the word as a constant value, we have a position of the landmark in the robot frame that is. That it comes from the mean vector, from the mean value. Indeed, the formula is the one that you see also in the localization exercise. The only difference is that here we have landmark me, which corresponds to two entries of the mean vector, which is the mean vector of the state distribution. We are taking the correct elements by using the ID state variable. Then what we do is we update the H matrix by adding at the end of it this measure prediction, and then finally we can compute the contribution of this measurement to the Jacobian function. And in this case, we have that according to what you have seen also in the slides here. Let me see where it is. Here. In the slides, we have seen that each measurement contributes to the Jacobian by a row vector that is as high as 2, because the measurement is the position of the landmark in the robot frame, and as large as the number of variables. And this is what you find here in these zeros, 2 dimensions of the state. And then, as you can see from the slide, you will have to fill in the first 3 columns by putting there minus the transpose of the rotation matrix and the product of the derivative of the transpose of the rotation matrix times the vector, which is given by the difference of the landmark position and the robot position in the robot position, which you can retrieve from the homogeneous transformation. And these 2 elements are going into the first 3 rows of this matrix CM in the MATLAB code. Then you will have to fill the elements in this matrix corresponding to the landmark block. And in the slide you see that in this case you will have to write the transpose of the rotation matrix in correspondence of the landmark block. So what we do in MATLAB is we use the ID state variable, which contains the position in the state vector where the landmark is to be found, and in correspondence of ID state and ID state plus 1, we write exactly the transpose of the rotation matrix. Again, this is MATLAB syntax for saying that we are going to fill all the rows, columns, number, ID state, and ID state plus 1, for a total dimension of 2 by 2, which is consistent with the transpose of the rotation matrix. Then the matrix, the whole matrix corresponding to the Jacobian of the observation is obtained by stacking all these elements together using the MATLAB syntax n plus 1. Then what you are asked to was to fill the observation noise by using the formula that you find on the slides, in particular here, okay? And then after the observation noise was done, you were asked to write down the update of the covariance, which you can do by using these formulas that you find on the slides. It's the 3rd slide, where you have the recap of the extended Kalman filter. And if you go here, you see that we have filled the Kalman gain and consistently the formula for the update of the covariance matrix. This is all for the correction. Very briefly, I will go through the add landmarks function as well. In this case, you were already given the initial part where we retrieve the state of the robot, both its position and its orientation in the 2D plane. We compute the rotation matrix, and then we retrieve how many landmarks are observed and store this value in the m variable, so that we can then have a for loop over all the landmarks observed, where we can update the state vector by adding the new landmarks. So what we do is we retrieve the measurement structure corresponding to the ith observation in the for loop. Then we retrieve the state position corresponding to the landmark identifier, and in case this state position is equal to -1, then the landmark needs to be added, because, as I was mentioning at the beginning, the ID to state map is a vector that at the beginning of our simulations has all -1 values. So in this function, we are going to first check that the landmark was never observed by checking that the entry in the ID to state mapping index equal to the identifier is equal to -1, and then once this has been done, we can update both the ID to state map and the state to ID map by writing the corresponding entries. In particular, we need to write that the ID of the landmark corresponds to a specific position in the state, and also the opposite mapping. Then, once we updated the ID to state map and the state to ID map, we can compute the landmark position in the robot frame. By the landmark position in the robot frame, it's just retrieved from the measurement, structure. What we need to do is to use the current estimate of the state, namely mi of t and r, in order to write down the current best estimate of the landmark position in the world. It is the best that we can do to initialize the mean value of that particular landmark, meaning that we get a position of the landmark in the robot from the measurement, then we use the homogeneous transformation corresponding to the current estimate of the state to get the landmark position in the world. And this will be our initialization of the mean value of the landmark. At this point, only the update of the covariance is needed. We need to add the block corresponding to the new landmark, and we do this by filling with all zeros in the columns that are outside the diagonal, and on the diagonal we will have this block corresponding to the new landmark, where in principle we should propagate the covariance of the state and the covariance of the measurement using what the professor has written on the blackboard. But in this case, we are using a simplified assumption, and we are just saying that we can initialize the covariance of the landmark by using a sufficiently big value, and that then by subsequent observations we will refine the value or the mean value of the landmark, and also refine the covariance matrix, which will become smaller and smaller as you see when you run the program. Okay, so this was a necessary explanation, because otherwise you saw something on the blackboard and then you see something different in the code. So it is perfectly legal, it's just a simplifying assumption for this particular exercise. In case you want to go a little bit deeper into this, you can revise the slides about fine transformation of Gaussians and update these two rows using the machinery that the professor has just shown. Okay, so Now, you have already seen how but I will do that once more. So I am in the 10 EKF SLAM folder. I'm running Octave EKF SLAM and taking from the other screen. Okay. And here you see the robot is the green square with its covariance. You have the landmarks with their covariance. Landmarks that are currently observed are represented as blue circles. And as you see, they are initialized with a very big covariance matrix. Now it will sense some landmark here, yes. And you have seen that we have initialized its covariance with a big value, and it's actually a circle because we are giving a covariance matrix that has no preference between the two axes. So this is the execution of the program. This is what you should see at the end of the exercise. I hope you managed to did this, at least the prediction part. Anyway, you can always write an email if you have some doubts, and I will publish the solution right now so that you can check it.
We are on the phone.
And at this point, we will stop the streaming as it is already.
Already done.
Yeah, already past 1. Yes. So I'm stopping the streaming.